Good afternoon, sir, honorable speakers, guests, and professors, and the research scholars. I'm Turaman from Lincoln University, Malaysia. And today, in this conference, and I'd like to present about the topics of numerical investigation on the buckling behaviors of Coffonsty, Bailout-Bos, Salenda columns. So in my presentations, it comprises 8 sessions, starting from introductions, methodologies, findings, results and discussion, conclusions, limitation, suggestions, references, and the question and answers. So as the introduction said, so I'd like to start from the background of the research. So my research topic is focused on the behaviors of Coffons steel. So Coffons steel is a kind of steels manufactured at room temperatures with a thin sheet of steel coins. So nowadays in construction industries, the builders and engineers began to focus to use the Coffons steels in place of the conventional materials like the woods, timbers, and hot rolled steels because of their high strength to weight ratios, because of the eco-friendly nature and easy for installations. So here in this figure, so we can see the applications of Coffons steel in building constructions, not only as the non-structural components, but also the structural members. So here in this figures, we can see the falling down of the tower columns and also the leakage of the white tangles. This is because of the structural instabilities of the members, and this type of instability is called the bucklings. So here, this type of buckling is called the global buckling, and this is called the local bucklings. So for applications of the Coffons steel member as the structural components, the major challenge is the bucklings. So this may be the local, distortional, global, or sometimes there may be the 2 or the more types of most of the combinations of the bucklings. So here in this figure, so we can see the nature of the buckling of the compressive member columns. So in the first figure, we can see the column member is stable. So because the perturbation load is equal to the critical buckling load, so the member is stable. But the perturbation load becomes greater, the member became unstable and buckle to the right side. Here we can see the lateral displacement delta U. So here in the last figure, we can see, so from until the dead points, the column is stable because the equivalent of the perturbation load and the critical buckling loads. But from that point, the columns have become unstable and it can buckle to the right side or the left side. And this point is called the bifurcation point. Whenever we consider about the instability of the compressive member, the bucklings, we have to concentrate the focus on these influencer factors like the end conditions of the member, eccentricity of the loads, geometric imperfection, and the slenderness ratio. So here's in this figure, so we can see the cross section of the Coffons steel members. So in the first 2 rows, they are called the single detached members. Single detached member, and in the last row, we can see the combination of this single detached member, and this section are called the Bailout members. So whenever we use at the structural members, the literature endorses that Bailout Coffons steel section have the higher strength than the single detached sections. So through the recent investigations, so we have found that most of the researchers were focused on studying the bendings and the flexural behaviors of Bailout beam members, and the very few researchers focused on the compressive member columns. So in 2011, Reese investigated the friend-to-friend Bailout-Bos with the CM wall condition and suggested the applications of modified slenderness ratio. And in 2013, Liam studied the failure modes of different types of Coffons steel singles and Bailout member at C, box, double box, and I section with the numerical software Abacus. In 2016, the NNT applied Abacus software to assess the nonlinear analysis of Coffons steel Bailout-Bos double angle columns with pin-ended conditions and a compression load. And in 2018, Marshall applies the Abacus software to examine the nonlinear analysis of Coffons steel channel section, column and the compressive loads, and calculated the load-bearing capacity and influence of imperfection and load-bearing members. And in 2019, Krishnanu investigated. There has been no previous work described any Bailout-Bos Coffons steel section or friend-to-friend connection through the bowl or screw and a uniaxial compression load. And in 2021, Mon and Salvans recommended to compare the modes of buckling among the Billard-Bowes sigmas and I section through the uniaxial compression load for global buckling as the vertical structural members. Based on these reasons, significant of the research, here's I have found the 4 research gaps for this study. Gap 1 is that most of the previous researchers were focused on co-forcing Billard beams member for their bendings and flexural behaviors. As the gap 2, there has been no previous work described by any Billard columns by means of Billard weld connections. And as the gap 3, for numerical analysis software or finite element analysis, most of the researchers use the Abacus software to investigate these behaviors. As the gap 4, numerical results for the Billard-Bowes and I columns by means of ANSYS need to associate with experimental method. Based on these 4 research gaps, here's I have found the 5 problem statements to analyze this study. The first one is that to Billard did the section members, so by means of the Billard connections, weld spacing became the significant details. This means that we have to know which weld spacing will be the most applicable spacing to create the Billard member. This is the research question 1. The statement 2 is that for the end conditions, which type of end condition for the compressive member is favorable to use for this analysis? Did you see there? Statement 2. And the statement 3 is that which form of Billard column is more preferable to apply? It means the Billard-Bowes column or I column is more preferable to use as the structural members. And for the section 4, based on the difference of the height of the columns, maybe the short column and long columns, the question is, are the modes of buckling the same or varies? And the last one is the external reliability of the finite element software ANSYS for the design optimization for this type of buckling columns. Based on these problem statements, so I have made this investigation. For the problem statement 1 and 2, it is already solved and already presented in the last year of International Conference of Sustainable Developments of Material Science, Technology, and Engineering 2022 in Malaysia. And I have found the 2 findings. One is the best weld spacing for the filler weld connection. There is a 509.6 millimeter. It's the best weld spacing. And for the end connection is the use of end plate at the end of the column is better than for the column without using all the end plate. So these 2, the statement is already identified. For the statement 3, it is also identified that the Billard-Bowes are more preferable to I column, and this article will be published in the Scopus Index Journal, International Journals of Sustainable Construction Engineering and Technologies. For the problem statement 4, so for the short column stats, the local buckling govern. This is already identified and already published. And now in this conference, and I will present the how global bucklings are governed for the cylinder columns. And also for the problem statement 5, so the use of the numerical software ANSYS and compare the results with the recent experimental output in this conference. So the objective of this research begins to investigate the buckling behaviors of Billard-Bowes cylinder columns by means of the numerical software ANSYS 2020 R1 and compare the results with experimental output for design optimization. So the methodology here I use the numerical method of the finite element software ANSYS 2020 R1. And this is the reference finite element model. So this model is a reference for the recent research of the experimental method done by the Christianu et al. 2019. So from this experimental model, here I use as the reference model for this numerical investigation. This is the geometric section of this reference model in this investigation. Here B75L 70,000 when represent the name of the specimen in this investigation. 75 represent for nominal web dimension. L represent for height of specimen. 70,000 represents for nominal height, and the 1 is the number of the tested specimen. And these are the material properties for this numerical investigation. For this prescribed linear and nonlinear analysis. This is the finite element mesh model of the Billard-Bowes cylinder columns. These are the statistical data that are used in this analysis. These are the results of this model. And for the 10 mode of buckling for the linear and nonlinear buckling load. Here, the fast buckling mode governs for this investigation. So its value is 17.24 kilonewton for the linear buckling and 17.22 for the nonlinear buckling. And the global buckling governs for this cylinder columns. From this finding, here we can compare the three results of the analysis, the numerical results, experiment results, and the analytical results. Here, the yellow color represents the value of the cylinder columns. The value of the cylinder columns.
Me, sir,
for the numerical result, it is 17.24 kilonewtons. Experiment result is 90.55, and the analytical method is 70.1 kilonewtons.
Sir?
This is the results of this investigation. Here, the global buckling governs for this investigation. This is a research question, and this is the solution that I find in this investigation. Here is the two limitations for this studies. One is the limitation on the type of connections, and one is the limitation on the geometries. Based on these two limitations, here I gave the two suggestions, the recommendation for the further future studies. These are the two suggestions. These are the references that I use for this presentation. Thanks for your listening.
Thank you, sir. Thank you and congratulations for your presentation. So my question is, may I know your logical basis on conducting your numerical investigation? So I mean, have you experienced serious problem on why did you come up on conducting this research or the numerical investigation on both beams and columns?
Yes, thank you for your question, sir. This is because of based on our research
Sir,
question, research
you
gap.
can unmute your microphone because we can't hear you over here.
Pardon?
Hello, Sir Mon.
Yes.
You may unmute your microphone.
Hello, sir. Can you hear us?
No, I don't hear.
Okay, sir. I will just repeat the question. Can you hear me now?
Yes, I hear, sir.
Okay, sir. So here's my question again. So may I know your logical basis on conducting numerical investigation on the buckling behavior of the cold form steel built box slender columns? So I mean, have you experienced serious problems, and why did you come up on numerical investigation or on conducting this kind of research?
Yes, sir. This is because of the reason the research gap. Because so most the previous researcher gave the recommendations to give the comparison with the numerical investigation with the experimental output. Because the foremost researcher that do the experiments for this type of columns by means of experiment. That's why here I made the investigations by numerical method.
Okay, sir. Thank you po.